In this video, we are going to do some K-means clustering, and the data that we're going to use is this one here. It's on the machine learning repository at UC Irvine, and this is the data and estimation of obesity levels based on eating habits. And well, I'm going to be following pretty closely another video that I watched where I learned about K-means clustering. I'll link it down into the comments. But it's a YouTube channel called Trent Does Maths, or Trent Does Math, and he made a great video on K-means clustering, a project about it. So I watched that video to learn about it, and well, this project is kind of my attempt at trying something out myself. So you'll notice some similarities in the structure, but there are some big differences as well. But anyways, let's get started. So firstly, we're going to import a variety of libraries. I'll just import all the ones that we need. So pandas, matplotlib, seaborn. We're going to be scaling the data, so we're going to need standard scaler, then NumPy, and we actually need the K-means algorithm. And silhouette score, and finally this last one is so that the plots that we use, or that we create with matplotlib, we can kind of turn them around. What is it? Axes 3D, there we go. You'll see what this does. It just makes so I can use the cursor and turn the plots around. That's what it makes it do. What do I do? Oh, I probably did it again, hey? Yep, over there. That's a good start. Alright, well, I've already copied the path. Seaborn. There we go, alright. I've already downloaded the data, and I'm going to just read in the file, which I've already copied the path for me. That's the path for me. And then we're going to store it in a data frame, just calling it data frame raw, to differentiate it between the data frame that we're going to be using later on, which is going to be pre-processed and engineered. So we can use the read CSV function there, specify the path. Oops. And this is the data. So you can see it's got quite a few number of columns, and you can look at the web page here to see what all these mean, but we're actually not going to use them. All I'm going to do is use weight, height, gender, and age, and I'm going to cluster the that height, weight, and age. That's what I'm going to do. So we look at the columns. Well, actually, first we're going to create just a copy of that, and the reason being is because if we ever need to, well, for bigger data sets, it's actually quite a big deal to read in the data because it might take in a couple minutes. This one doesn't take a couple minutes because it's quite small, but it's good practice just to create a copy of it so that if we ever need the original, we can just refer back to it. So we do that, and we already took a look at the data. Let's take a look at the columns. Those are the columns. So there's actually not that many as I thought there was. But yeah, we're gonna take these ones, just the first 4. So we can do that by just specifying the columns like this in a 2D array, 2D list, I should say. And then we'll just print out the info. So yeah, age, height, and weight, they're floats. Age in reality should probably be an integer, but the reason being that it's a float, we're just gonna leave it as is, but reason being is you can see that some of the ages, they have a lot of decimal points. I'm not quite sure why. Now I'm thinking that it's probably best to actually round these, but I'm just gonna stick to the plan that I had. Yeah, it probably makes sense to round these to the nearest integer. And the heights, like for some of these, they have drastic amount of decimal points. And the weight, I'm not sure why they do it like that, but so we can look at df.describe, and it tells us some information about that. So there's the minimum value for age, which is 14, the maximum is 61. The minimum for height, there's the minimum for height and maximum, that's reasonable. Now the weight being 39, that's probably for one of those ages that are around 14, 15, 16. So that makes sense, yes. If it was for adults, then I'd look at that maybe a bit closely, but and then the maximum is 173 kilograms. But now obviously this is a data set specifically looking at obesity levels, so some of the people coming in will be obese. That makes sense. So we have 173 as the maximum. Now what I'm going to do is split the data into male and female, because we're going to analyze those separately, because obviously the weight versus the height will look differently for men and women. So we can just create 2 different data frames and just take the values or the rows where the gender is male for this one, and then for the second one we just do it like that. There we go. So now we have 2 data frames, one for male and one for female. Then we're just gonna plot a histogram of the weights, the heights, and the gender to see how the distribution goes. And we can use matplotlib for that. So we specify the figure here and the figure size. I think this one works, but we can always adjust it if it doesn't look right at the end. And then we'll create a number of subplots. I think that'll be, 6, right? Yeah, for 2 genders, and then weight, height, and age. That's 3 times 2, that's 6. So on each row we'll do either height, weight, or age, and then for each column we'll do the gender. So we have 3 rows, 2 columns, and that'll be the first value. So we're going to create 6 subplots, or we can just do it like that. So all we change is just the index here. These first 2 values here specify the row and the column, and the third value specifies where the actual plot lies. So if you have 3 rows and 2 columns, you have 6 places in total where you could put the plots, and it just goes horizontally first and then downwards vertically. So this will be on the top left, this will be on the top right, this will be underneath the top left, this will be underneath the top right, and it will just go down like that. You'll see. So this first one, it will be male. We'll start with weight, then female weight, male height. You can see where I'm going with this. Alright, so like that. And then we just do the histogram, and that's just plt.hist. So we take the height, and then we can add a different color to it. Now, which colors do I use? I've got my notes next to me. Here I used aqua, black, like that. Alright, so the color will just be the color of the histogram, and then the edge color is just so we can differentiate the distribution a little bit better. That's just the edge of the bars. It's not meant to be like that, it's meant to be like that, yes. Okay, and then we do the title. And the title of the first one is distribution of male weights, like that. And then we'll just do the X label and Y label. So yeah, like I said, the reason we're doing this is because we're going to see the distribution. It's to get a good idea of how the weights, heights, and ages actually range. Like we know the minimum and the maximum, and we looked at the describe here, but it's much easier to visualize when we actually have a graph. So this should have been weight. Weights, and then frequency. Alright, so that'll be the first one. We can just copy and paste this for all of them, and then we'll just adjust them accordingly. Okay, and then, alright, what do we do? So female weight, so we just put the female there, and I'll just change the colors and edge colors to how I've got it. So for the females, I just put chocolate as the edge color, just to make it a little bit different. Then like that. And then male height, so we just change the column there. This one I'll put as gold. Distribution of male heights, just like that. Or we can just put weight and height there. Female heights, like that. This is gold, and we'll do chocolate. And then finally, age, which I've got as light green. There we go. It's going to be a lot of copy and pasting here because we're going to be replicating the plots and the visualization for male and female. But that's alright. So if I've got no errors, there you go. And yeah, you can see that the fig size is a little bit too small. We can see that the height of it is a little bit too small. It needs a bit more space. So we can change the height to maybe 12. That looks a little bit better. Maybe 14. We'll go 8 to there. There we go. That looks a little bit better. Okay, so we see that, yeah, while the male weights, they tend to be between 50 and 125, the female weights are generally much less, between 50 and 75, and then there's a little bit above 100, and that looks to be the female weights look to be a lot more strangely distributed. So this is a big variety in people, like in terms of their weights, huge variety, and the heights are much more normally distributed. That's pretty typical of heights. You get some really tall men over here up to almost 2 meters. Then the ages, well, mostly younger people, but there's a few older people as well, up to 60, 50. So you can see there's a big range of weights, especially. You have like people that are 50 kilograms and people that are 150. For male, you get up to 175. Yeah, big distribution. So you can see that, well, this is normally distributed, so that kind of shows that we might be able to use the standard scaler instead of the min-max scaler. So the min-max scaler is uses the minimum value, the maximum value. It doesn't really follow a normal distribution. There's other options as well, but the standard scaler is generally for normal distribution because it makes a mean of 0 and then a standard deviation of 1. But we'll use that later on. Now what we're going to do is use SNS, Seaborn, to create some box plots. And we can kind of just copy, we'll just, how do I copy the entire thing? I have to scroll down with this bar here because my cursor, or my mouse is being funky. When I scroll down, sometimes it scrolls up. But we'll just copy all this here, and just so that we can keep the subplots there. We're going to create a box plot now. We do that using Seaborn. Now I'll put this as, we'll keep it as 814. We'll see how it goes. And the code for this is just use the SNS library there and then put box plot. And for this we specify the data under the argument here, and the data for this one is just df male weight, and we can put the color as usual there. It's aqua. And we'll just put a title for this first one, just box plot of male weights. And that's what we'll just keep it as, just for simplicity. Okay, so we've got the first one, male weights. You can see the general structure of the code there, the function. Yeah, so we use df male weights, yep. And the second one we put as the female weights. The third one we'll put as the male heights. Change the color to gold as before. The second one is the female heights. Change that to gold. Lastly, we have age. Ages. This is. I wonder if I've got all these as it should be in terms of the titles. Male weights, female heights, male heights, male ages, female ages. And then this is like that. There it is. And the reason we're doing this is just another visualization. We can see how the range of the data goes. I believe another name for this is the box and whiskers plot. But yeah, you can see that the way these work is that the 25th and 75th quartile, the data between those is housed in this box here. So 25% of the data is less than this first line here, so it's down up to this bottom part, which is the minimum, then 50% of the data is below this second line here, which looks to be 90 for the male weights. 75% is the next line, and then we have 100. Well, actually, 100% is this point here, but the dot is separate from the box plot because it's classed as an outlier, because it's much different than all the other values. And if we look back at the histogram, we can guess at what this outlier is. It's this part here, because there's no other values between 125. Well, not 125, because 125 isn't the end of this this bar here, but between here and here, hopefully my mouse is showing, I believe it is, but if it's not, then I'm sure you can guess what I mean. So you can see that there's in the distribution of male weights, there's a little bit of a bar close to 175, and that's separate from the initial cluster of the other cluster of bars. So yeah, you can see that that's about 175, this dot here. There's no outliers for the female weights. There is some outliers for male heights. There's no outliers for female heights. And there's a bunch of outliers for ages. Now the outliers for ages, it doesn't really, I don't really consider it really much of a big deal, because it doesn't, I mean, age is somewhat indicative of the level of obesity someone will have, in some way, but not too much. But we're gonna analyze the outliers separately, and that's just so that the K-means clustering can work properly. So the way that the K-means clustering works really is by considering the distances between each point. So it chooses 3 point, or it chooses not 3 points, but we're gonna use 3 clusters later on. It chooses a number of centroids based on how many clusters you choose, just randomly, and then it measures the distances between those and each of the data points, and whichever the data points are closest to, whichever cluster the data points are closest to, it considers those as part of the cluster. And then that's the original just organization of it, and then to conduct an iteration, it will move the centroids, which is the cluster centers essentially, to the center, or to the average of all their data points, and then it calculates the distances again, and that means that it will change a lot of those clusters with each iteration. I don't really have a visual for you, but I recommend, if you don't know K-means clustering, to look up a visualization of it. That's going to be far better than just a vocal description. There's plenty of videos on YouTube about it. Right, but the point is that if you have outliers, I need to get back to the point. The point is that if you have outliers, then that changes the K-means clustering drastically, because those outliers will be well away from the clump of data, so it's going to change the way that the clustering goes. So really, you need to remove the outliers if you want a good clustering, and then you just analyze the outliers separately, and that's what we're going to do. So we've got the outliers now. Now we need to actually create some code to find these outliers. Like, we can look at them, and I mean, the manual way to do this would just be to go on the data frame and find where these points lie, but that's going to be way too tedious. That's fine. We can find the outliers using a bit of code, and we'll find the outliers for the weights here. So I'll just write down what outliers we're going to find here. So female weights over here. So we'll just do this first, and then we'll do the height and then the age. And now the way that we're going to do this is that, so the outliers, they fall past this final line here. And this final line is this value here, which is the top of the box, plus 1.5 times the interquartile range. And the interquartile range is just the height of the box, which is quartile 3 minus quartile 1. That's the formula for it. So anything past that point will be an outlier. And then equivalently on the bottom end, it's the same. So it's what is it? It's quartile 1 minus 1.5 times the interquartile range. So anything less than that will be an outlier. Now the reason that these two distances are not the same is because there's no value below this line here. If there was values, then 1.5 times the interquartile range, that distance would be the same for the top and the bottom, because you're just doing 1.5 times the height of the box. And you can see that with the heights here. So these distances are roughly the same, where you have these lines separate from the box, and that's really how it would be if there was data enough in both directions. But for the ages, there's no data below this line here, so that's why that stops short. So really the outliers wouldn't be anything less than this line here. They'd be anything less than maybe somewhere around here where my cursor is, so a bit below. So we need to find the quartile 1, quartile 3, interquartile range, and then we'll just do the, we can just do the I don't know what to call it, we'll put it in there because I don't really know I was going to create a separate variable for 1.5 times the interquartile range, but that's really not that big of a deal. Okay, and the way that we can find the quartiles for here is by just type in, I meant to say quantile. I think another name for them is quartile, actually. Maybe I'm wrong with that. I've always just called them quartile, but that's fine. But we could write quantile here, 0.75. So that'll be the quantiles. And if we actually just print this, let's just print Q1. You can see that's 75 for Q1, and if we look at the weight, then the bottom line here of the box is about at 75. So if we look at the quantile 3 for weights, then it should be about 110. If I looked at that right, yeah, and about 110. There you go. So then interquartile range is just Q3 minus Q1. And then all the outliers for DF male for weight will just be, I'll just write the code here and then I'll explain it. It will make a lot of sense, I think, once I write it out. Okay, there you go. I believe that's the code, yeah. And there should be one outlier for this one. Yeah. So yeah, we have a weight of 173, and that's this point. Oops. That's this point up here, 173. Okay, and the way that this works is, So we're taking a look at two situations. One where it's less than the bottom line here for weight, though. But I'm not going to scroll up to show that one. I'll just do it for age here. So it's where it's less than the bottom line or above the bottom line. So this first section here is where it's less than the bottom line. So it's an outlier on the bottom section. So it's low relative to the other data points. And that's where the weight here for DF male is less than quartile 1 minus 1.5 times the interquartile range. So that's the first one, where it's all the outliers that are below the data points. And then the second one is where all the outliers are above. So it's where the weights are greater than quartile 3 plus 1.5 times the interquartile range. And now this bar here is just an OR. It's a logical OR, which means that we're taking the values where it's this part here or where it's this part here. Because essentially we want the outliers for both, where it's above and below. Now we don't have any outliers for below for any of these actually, in fact, but just for consistency, we'll do the whole code here. So that's going to return a bunch of true and false values essentially, because it's going to return false for all the times where the condition is not met, and it's going to return true where the condition is met. And where it's met is where we have the outliers. So then we just put it back into this data frame here, and it'll run through. So let me actually show you what this looks like here. Just the condition there. So yeah, we have a bunch of falses and trues, and somewhere between there's a true, which is where the outlier is. It's in fact it's 344, row 344. But you can see it does this for every single row. So when we put it back into the data frame, we're essentially saying we don't want row 2, we don't want row 3 because it's going to be false, we don't want row 4. And then where it says true, we want that row, which is this one. That's why it's returned this row. And then we don't want all the other rows. So that's just kind of a high-level description of how this... I don't know what this actually called. There's a technical name for it, but how this way of editing a data frame works, essentially. All right, well, we've got the outliers for male weights, and now we just copy and paste it for female weights, and we just change all the males to the females. There's a lot of them. There we go. And then we just do the same for height and age. So we'll just do male age here, and then I'll just copy that afterwards. Oh, sorry, height. Height. This one's easier because you just change the W to the H. Over here as well. And then female height there. This one's actually not so bad because you just add an F and an E. There we go. And then finally we do age. And for age there's going to be a lot of outliers. Or age height, that doesn't make any sense. Male age. There you go. There we go, and then female age. And what I'm going to do after this, I'm getting ahead of myself, let me just finish this first. Okay, what I'm going to do is, I'm going to delete, well, actually I won't need to do that. I had it on my original notes, but I was going to delete the variables Q1, Q3 and IQR just after every run through because they're getting repeated, but I could do it at the end here just because we're not going to use them again, And then like it's really just confusing. If we write Q1, Q3, or IQR, then obviously they're going to be different for every single situation. There's going to be 6 different Q1s, Q3, and IQR. So, which one do they refer to? So they're really just temporary variables. So we can just delete them after that. Just minimize any confusion if I write them again. All right, so now we've got the outliers. Now we're going to create some variables of combinations of outliers. We're going to take the intersection of the outliers, which is all the outliers that are a part of every single variable here. So the outliers that are for weight, for height, and for age. And the reason being is that we can see where there's quite a drastic outlier. So the outlier just for weight will be slightly away from the data, but then the outlier, if there's an outlier for weight, age, and height for one individual, remember each row is one individual, one person, then that's going to be drastically away from the data. And we can analyze that a little bit differently. Now I'll give you a spoiler, there are no such cases, but we're also going to do the union, which is all the outliers. So we're going to create a data frame which has rows for all outliers, regardless of whether it's weight, height, or age. And I'll just write the code here. I'm going to firstly create indexes of create variables corresponding to the indices of all the outliers, all the rows. So you'll see based on the variable name what they actually are. So the reason being is because when we actually do the intersection, the union, their function performed on the actual index rather than the row or the data frame itself. So we need to convert these to indices. So here we're just creating a variable called index male outliers weight. So it's all the indices corresponding to the outliers. And if you remember, the outlier here was 344, so that's the index. So this variable, it's going to contain just 344. If there were more rows, then it contain more of these indices. So we're going to do this for every single situation. Remember there's 6. So df female outliers weight, then df male outliers height, like that. Then female height, then male age, and finally female age. I did something wrong there, didn't I? Yeah, I spelled it wrong. df female outliers weight is not defined. Okay, what did I do here? df female outliers weight. Oh, maybe I didn't press enter here. There we go. Yeah, I didn't run the code before. All right, and now we're going to create we're going to union the. Look, I had in my notes to union just the weight and the height, which is more. It's the outliers that actually matter more, right? Like you really want to know the outliers for weight and the outliers for height. The outliers for age doesn't matter too much, but I wanted to do a K-means clustering for 3D. So, I mean, it just makes sense to do age as well. So that's why I'm just going to do age. Well, we're just going to union all of them together. Oh, but it's actually a bit cleaner if we do it separately. Kind of just talking to myself here, but If we do, actually, I'll show the intersection of it first. I'll show you that there are no outliers that are combinations of all of them. And then at least then you'll see the code. So it's intersection male outliers height. So I'm actually not going to do the intersection of all three, even though that would be the what I'm looking for, because if you have the intersection of the weight and the height and there are no values, then there's no point in doing the intersection of weight and height and age, because it's not going to add anything to it. I kept calling these functions, they're actually attributes. So yeah, you can see that there's no indices that are intersections of both weight and height, so there will be no indices that are intersections of weight, height, and age. And we can do the same for female here. We actually don't even need to store it in a variable because we don't actually need it. But yeah, you can see for females as well, there's no outliers in common. And that's the spoiler I was saying before. So there's no oh, how do I redo cell operation? There we go. There's no point in analyzing the intersection. We're just going to analyze the union. So we're going to create the union of weight and height. And the way that we do that is male outliers weight dot. We just use the union attribute instead. So that's weight and height, and then we do for the female case as well. There we go. So that's just the union of weight and height. So now we need to find the union of weight, height, and age. And the way we'll do that is just to union the weight and height with age. And the order doesn't matter. If you take the union of A and B and then C, it's the same as union of B and C and then A. Age, there we go. Do I have this right? Yes, I do. Good. So we can actually, we'll call this first and then we'll see what values we have for the union. You can see that we have a lot more indices here, but not relative to the number of rows in the original data frame. I didn't show how many of those are, but if we look at info, we can see how many rows there are. I think there's like 2,000, or just a bit above 2,000. Oh, 2,000 in total for male and female, but about half for each. Yeah, you can see how many entries there are. Oh yeah, 2110, there you go. So most of these indices corresponding to the outliers there for age. You see there's a lot more outliers for female ages. And the reason being is that if we look back at the age here, the distribution is much more focused in this section here. And consequently the box plot is lower. And then consequently the 1.5 times interquartile range value is smaller, which means that a lot of those ages will be outliers. So you can see that if we had the line for the female ages here, where the male line goes, then we'd have a lot less outliers. But all these values here where my cursor is, they're going to be outliers now for the female because they're outside of the box plot, the entire box plot, and the whiskers. I assume that these are called the whiskers. Alright, so we've got the union of those, and now we're going to create variables, data frames for the inliers. I think they're actually called the inliers, but it makes sense if you don't have outliers, you have inliers. So I'm just going to call them that, and this one's not going to be an index, it's just going to be the inliers, and we're going to drop all those indices for the union. And the reason that we're doing this is because when we do, like I said, when we do K-means clustering, we don't do that for the outliers. So we need a new data frame which only contains the inliers. And that's what we apply K-means clustering to. So we're dropping all the indices for the outliers, and we're dropping the union because that's going to contain all the outliers. And we're going to do the same for female. There we go. And we can create a separate data frame for the outliers as well, for the union of the outliers, which will just be all the points where the indices for the outliers are. So that's this one here, dot location essentially, and then these indices are the indices corresponding to where the outliers fall. So we're just taking those indices, applying it to this data frame, which is data frame male, and that's just going to be the new data frame containing only those rows that are outliers. And we do the same for female. Oops. What is it? Dot lock. Oh, I was meant to do the square brackets. That's right. There we go. Alright, now we have the data frame here, which will contain all the outliers, and you can see that, I mean, you can kind of guess at which outliers these are. This one's obviously for weight. This one's for height. 197. I'm just guessing. It could actually, or no, it won't be for weight and height, because if you remember, we didn't have any intersection of the two. We have some for ages probably as well. 56, maybe that's an outlier for age. 55. And then female, remember we had a lot more outliers here. Yeah, so there's even the ... here, which shows that there's a lot more. 96 rows. How many outliers for male do we have? It doesn't say, but it's a lot less than the female ones. Well, we can see how many by just writing .info. Oops. 29 compared to about 90. Okay, so we have the outliers now. Now we can actually perform K-means clustering, but before, we actually want to get an idea of what the data looks like. We're going to create a 3D plot for that, and we're going to create a 3D plot of the inliers, and we're also going to compare that to a 3D plot of, of all the data, including the outliers as well, and we can see how this changes the data, and then you can see, we can guess at how K-means clustering will be affected. Show you what I mean. So we're going to create a 3D plot, and we do that with matplotlib. Alright, so figure size, or fig size, 10. I might end up cutting this out. Yeah, I'm going to write it and I'm going to cut it out. All right, so this is the code for plotting the 3D plot of weight, height, and age. You see that we'll have 4 different axes there, and those are corresponding to weight, height, and age for male and female, and then all the data, and then just the inliers. So you're going to have 4 because it's 2 times 2. So this first plot here is for male weights. This second plot here is for male inlier weights, so not the outliers. This third one is for female weights, and then female weights, heights, and ages. And it's the inliers. So if we run this, we can compare the graphs here. So you can see that if you include the outliers, which is the left one here, you can see that there's all these points here away from the data. And that's going to contribute heavily to the K-means clustering because that's a big distance. So for example, this data point here, if you had a cluster that had to include this data point, it would be skewed to the right quite considerably because it needs to be closer to this data point. Now compared to if we remove the outliers, you can see with this data that the outliers are removed. The clustering doesn't have to consider this data point here that's far away from the clump of data, so it's not going to be skewed quite. It's not going to be skewed at all actually in that direction because there's nothing to skew it, and that means that it's actually going to be indicative of how the data actually runs. Because when you have outliers, that's not normal, right? It's outliers by definition is anything that's not the typical case. So we want to actually run clustering for something that is the typical case, and that's the inliers, if that's the correct word for it, but it's not the outliers, right? And then we just consider the outliers separately because they're kind of the not the normal, right? It's not not what typically happens. So what typically happens in this case is this big clump of data here, and then these dots outside of here, that's the outliers. Anyways, that's for male inliers and male, and then we have female down below, and we can see that it's the same situation, right? Like for the left one, you can see all these points which are outliers, and then with the inliers, we removed all those points. Next, we're going to do the K-means clustering. And the way that we're going to do that is, firstly, we're going to have to scale the data. Because if we look at the axes here for weight, height, and age, they are quite different from each other. And K-means clustering will look at that, right? So if you have these values here, 40, 60, 80, 100, they're going to contribute much more heavily than 1.5 to 1.55 to 1.6, because the difference between those is 20 for weight, and the difference between each interval for height is 0.05. And the values are a lot smaller as well. For age, it's not too much of a big deal, but still, we're going to do the same thing. So we're going to scale the data and make it more consistent, right? So we're going to do standard scaler for that, which makes all the data have a mean of 0 and standard deviation of 1. So essentially it makes it follow a normal distribution, and you can see from before, if we look at the distribution of male heights and female heights, that follows very strongly a normal distribution. Age, kind of, it's left leaning, but and then for weights it's slightly left leaning for males, and then for female it's just kind of all over the place. But it's close enough that I'm happy to use a normal distribution with it. If you want to find the formula for it, you should search it up. But yeah, I'm not going to show it here because there's plenty of better visuals for that you can find. But essentially it turns it into a normal distribution. It makes the mean 0, standard deviation 1. There's actually a specific word for it. I forgot. It's a normal distribution, but maybe it's a standard normal distribution, I think it's called. Not sure. But in any case, let's get the scaling happening. So we're going to use the sklearn library for that. So we're going to import I'm going to create an object here, or an instance. Standard scalar, which is the class. And then we're going to fit and transform the data. So we're going to fit and transform the inliers, because that's the data that we're going to be that's the data that we're going to be applying K-means clustering to. And the way to do that is to use scalar.fit transform, and then we pass in the columns that we actually want to fit and transform, which is weight, height, and age. And remember, we still have the gender column, which is it's not really necessary considering we write the gender here, but actually that'd make the code a lot simpler if I remove that column, that feature, but I'm just going to stick to my plan here. So this one here is going to return a NumPy array. If we just run it, I spelled that wrong, didn't I? Transform, not transform. There you go. So it returns a NumPy array, and each column here refers to weight, height, and age. We actually need to convert that into a pandas data frame. So we'll just store that temporarily in this variable here, because we're going to add another array here, which is just for the male gender, and then we're going to add that to the data frame. So we'll have the same format as before. So essentially it's just going to be an array consisting of a column of strings where it just says male. So we convert this to NumPy. Oops. And then we're going to reshape it to a column like that. Or I believe actually it might even be a row. Let's find out. No, it's a column, yeah. And the reason being is that we're just going to create an array with the combination of these, and then we're going to change it to a data frame, just so it looks a little bit more neater. I think it's neater anyways than turning this one into a data frame and then just adding this one. But to each their own. Alright, finally we're going to convert it into a data frame. But first we need to actually stack the arrays. So we're going to do a horizontal stack here, and that's going to be stacking the gender, because that was the first feature. And we're going to stack that with the scaled inliers. So this section here, that will just create a new NumPy array with the gender and the inliers scaled. If I show you what this does, you'll see that it's just, there you go. So it's just an array where the first feature, it's kind of hard to see in this situation, but because the values are too long. But yeah, the first feature column is just male all the way through, and then the rest is the inlier scaled values. Anyway, so pd.aframe will go to a new line and we'll specify the column names, because otherwise the column names won't be shown over. So the column names are just gender, weight, height, and age. There we go. And we'll actually create, for all these columns, just the scaled thing, although gender's not scaled. Just like that. Just so that we can kind of differentiate them. Alright, well, we've done that for males. Now we're going to do it for females here. And the way that we're going to do that is just copy and paste and change every male to a female. There you go. Just write FE at the front of everything. Oh, that's a lot simpler than I thought it would. Okay, so now that we've standard scaled that, there is one more addition that I'm going to be doing, and I'll show you why. I should probably take a break after this. But first I'll show you why. So if we look at df Mayo inline scaled, and then we try to take away a specific column, like weight scaled, you can see that it returns a data frame, which is a little bit strange. And the reason is because it's something called a multi-index. If we look at df Mayo and we just take weight, for example, it returns a, what is it, a series, I think it's called? Yeah, it returns this, and if we do inline scale, it returns this. And it might not look much here, but later on when we feed it into K-means clustering and then various plots as well, that's actually going to be an issue. It's going to be an issue because if we pass it in as a data frame, some of those functions and attributes don't take in data frames, they require a series. So it just leads to a lot more complications. And when I first saw this, it took me a while to figure out what was actually happening. But if we look at df Mail and we look at dot columns, we can see the columns and it specifies it as an index. But if we look at this one here and find the columns, and you can see it's a multi-index. And it's just multi-index is a way to create a hierarchy of indices. And in this case, the multi-index is within the columns. Sometimes it can be within the indices, the index, but yeah, it's within the columns. So there's a hierarchy. And I think that standard scaler creates it just naturally when you fit and transform it. Even when I believe that even when I just put standard scaler into a data frame just straight away rather than doing this ordeal, it still did the same thing. But it's much better to fix this and change it back into a normal index early on, so that later on when we do the visualizations and K-means, we don't have to put extra code there. And I use a lot of ChatGPT with this. This helped with a lot of errors that I got. So we change the columns essentially, and the way we do this is just put get level values into 0. So we just take the 0th, I believe this just takes the 0th values, and for a multi-index there's more than one, right? There's more than just 0. So if you take just the 0th, then it changes it from multi-index into just a single index, because we're only taking this one value here. And in any case, this fixes it. We have female here, and if we run this, we can see that now it's just a normal index. And if we take weight scaled, then now it's normal. I'm actually going to show you another thing because you might find this useful. If we don't do that and we just keep the multi-index, you can see that's multi-index, scaled. There you go. So you can see that's the multi-index here. When we try to take specific rows of a data frame like this, greater than, let's say for all the ages that are scaled greater than or equal to 0, you can see it returns something really, really weird. So if we don't convert it back into an index, then you're going to have trouble with trying to find specific rows. So when we do it like this, we're trying to find all the rows where age scaled is greater than or equal to 0. And you can see that it finds some of these points, but then it doesn't take the whole row. It just takes those values. Usually it should take the whole row. If we just find df male and we do all the ages that are greater than 30. So obviously this one's not scaled, so the value is different. So yeah, it'll take all the values where the age is greater than 30, like in the entire rows. And this one's a normal index, but the multi-index doesn't do it like that. So that was originally what made me find that issue. Okay. Okay, I'm gonna take a break and we'll do the rest another time. Alright, welcome back. Well, for you it's going to be part of the same video, but welcome back for me. I'm going to continue off where I left off. So where did I leave off? Yes, we scaled the male inliers and the female inliers data sets. And now I want to plot them. So I want to plot the inliers versus the scaled version of them, so we can compare how they look like. And they do look pretty similar. In fact, the only difference that should be with the inliers versus scaled is that the scaled has different axes, right? So that the axes are all the same. That being said, I'm not sure if there's actually any differences in the shape of the graph. There will be in the plot, but that could just be I don't know. Anyways, what I'll do is I will pause the video and I'm going to plot male and female weights, heights, age, inliers versus inliers scaled. Hopefully that makes sense. So we're just playing for male and female. We're playing weights, heights, and age. So that's one 3D plot. We're going to do inliers versus scale. So there's going to be 4 plots in total. I'll pause the recording, or I'll edit this out, and then I'll explain the code. See you then. Okay, we're back. And let me just explain the code real quick. So we've got a figure creation here where we specify the plt.figure. And then we create 4 separate axes, all 3D-dimensional axes. And the scatter plot is pretty much the same for all of these. What we'll do is just create a plot for axis 1, and in the first case it's plotting male inliers weight, height, and age. Pretty straightforward. And in the second plot, we're plotting weight, height, and age, but scaled for male inliers. Third plot, we're plotting female inliers, weight, height, and age. And then finally, the fourth one, we're plotting the scaled version of those. So if we run this, we get 4 separate plots. And actually, yeah, I was mistaken. So I thought that the scaled version is different, like the shape of it, but no, it's actually the same, which makes sense because all we're doing is we're just scaling the data points down so that the axes are consistent. So the differences between, like for example, here we've got, for weight, we've got differences of 20. For height, we've got differences of 0.05. And then for the scaled version, we've got them closer, right? So for the weight, it scales by 0.5 with every step. For the height, it scales by 0.1. But it's not really the point of scaling to make the axes the same. So really what I should say is that it makes the data points scaled, so that the distances between the data points aren't crazy different from depending on which axis it's going. So the x-axis, the y-axis, the z-axis, the distances are scaled down, and that way K-means algorithm can run properly, right? It won't contribute heavily for one direction that it shouldn't. You know, for example, the weight here, because the values are much higher and the distances are much higher, I believe that's the x-axis there, so that axis will contribute much more heavily for the K-means algorithm. But once they're scaled, it doesn't. We can see that the shape is the same, but the values are just different, that's all. Okay, so now that we've plotted this, we're going to do K-means clustering now. But we're going to find the number of clusters that we should actually choose. Now, just based on my observation, it seems that maybe 3 clusters would be ideal, or 4 clusters. That's actually what we will use. We'll use something like that, but we'll try a few values. But we're going to do an elbow plot first, which is basically we test a bunch of number of clusters, and then we see how the error score changes. And we choose a reasonable error score, a reasonable number of clusters corresponding to a certain error score, or some other metric that makes sense. And we're not going to choose the lowest one, because the lowest error score will probably be the highest number of clusters, up to the point where we get the same number of clusters for however many data points there are. But that's just excessive, and that's meaningless essentially as a clustering technique, because you can't derive any meaningful observation from that. So you need a decent amount of clusters, but not too many that it's just meaningless. Okay, we're going to specify the maximum number of clusters here. So here in this cell, we're going to create an elbow plot, and you'll see why it's called an elbow plot. But essentially, well, I'll tell you roughly why it is now, and then you'll see once we actually graph it. The elbow plot, the error graph will look sort of like an arm, and we take the elbow of that. It's hard to really explain without visualizing it, but you'll see. Max number of clusters we'll set as 20, and then I'm going to, just because we're going to have to write the data quite a number of times, we're just going to store it in something simple called df data. And we'll start with male inlies scaled, and what we're taking is we're taking the weight scaled, the height scaled, and the age scaled. So essentially, well, this is what we're going to run K-means for. But now we don't have to write the whole deal here. We can just write df data, and that's just a temporary data frame for now. So we're going to specify the range of the cluster, which is just going to be from 2 till 20. If we have a cluster of size 1, that's just going to be the entire data set, which doesn't really make any sense. So a reasonable clustering technique will start at 2. And not to 20, we're going to go to max cluster plus 1, like that. You might hear me sipping on some liquid during this recording. That's just milk. It's my breakfast. So I don't know if the sound of me gulping it down will be loud, but if it is, well, that's fine. At least you know what the sound is. So then we're going to do a couple scores. We're going to do the silhouette score, which is a measure. Actually, I completely forgot what the silhouette score represents. I probably shouldn't do it if I don't know what it means. Yeah, I'm not going to use the silhouette score because I completely forgot what it represents. But for now, we'll just keep it simple. And typically, the simple case is, well, the silhouette score doesn't really create an elbow anyways, it doesn't create an arm. So it's got something to do with a ratio of the distance between points to points in other clusters versus points to points in one cluster. So it measures essentially how separate the clusters are. I should look into this a lot more, but we'll just stick with what I know more about. We've got the inertia here. So these are just the values of the errors, which is the distances from the cluster center to each of the points, which we're trying to minimize essentially. So with each iteration, this should minimize because we get the cluster center closer to the corresponding data points. So therefore the sum of the distances, this will minimize or will reduce with each iteration. If you don't know much about it, just watch a quick video on scores inertia with some visualization. That'll probably be a lot better in explanation. But we're going to loop through each of the values in the cluster. So we're going from 2 to 20 because this range, the range isn't inclusive of the second value here. So if we write 21, it'll go to 20. And we're going to run KMeans. So all we do is create an instance of the KMeans class, and we specify the number of clusters, and it's just going to be C. We're going to start with 2, then 3, then 4, so on. Then we're going to fit KMeans to the data. We're fitting it to weight scaled, height scaled, and age scaled. So really right now we're not actually doing KMeans for the purposes of doing our final clustering. We're doing KMeans for the purpose of testing what number of clusters we should actually choose. And the way we're going to do this is, well, firstly we're just fitting the KMeans to the data, so that runs the iterations. And then what KMeans will give us is the cluster labels, which is just KMeans.labels with an underscore like that. And this will be the, I believe it returns an array, but I'm not exactly sure what object it returns, but it returns the values for each data point, which is what cluster it belongs to. So the length of this will be the number of data points there are, and there will be numbers. Well, for example, if we have a cluster size of 5, there's going to be 0 through 4, and each of those values corresponds to the cluster, the specific cluster it belongs to. Now we're just going to append the score to the list variable that we created earlier, which is going to be KMeans.inertia underscore, and that's just the that inertia score, which is the distance, the sum of the distances between the cluster center or the centroid, same name, or means the same thing, to each of the data points. So we're just going to append it to there. What am I doing? Scores inertia dot append. And that's going to append it to this list here. So we're going to get a list of scores corresponding to each number of clusters. Now all we need to do is just plot the value. So the for loop will run and it'll create the list, and then we're just going to plot that one. So what do we got? Range cluster versus scores inertia. And I'm just going to write the title and the labels. So just to reiterate, the inertia is an error score, measurement of the error. Okay, that'll be enough. Okay, what do we got? that. See in range cluster. Oh, what am I doing? I already wrote the range there. There we go. Okay, you can see the arm shape to it. And essentially, now the reason I'm showing this is I'm going to show how we would interpret this. So if we're following this method where we're choosing the number of clusters based on the elbow of this plot, we would choose probably maybe 10, 11, because over here it starts getting more horizontal. So with every increase in number of clusters, there wouldn't be much of a decrease in error. If we actually increase this to, let's say, 40, you can see more of that situation there. So really we'll choose somewhere here, but in this situation I'm just going to pick 3 or 4. We'll pick 3, just because with this situation we're measuring well, the data points represent the weight, height and ages of people. So if we cluster it into 10 different sections, we can't really interpret that very well. It's just too many clusters. It doesn't really make sense given the situation, because with clustering we'd have to choose a number of clusters that makes sense. If we have too many, then it's harder to interpret. It just makes it more complex. We're going to choose 3 in that case, but just for completeness, I'll show you the same plot for the females. And that looks kind of like this. So you can see the elbow is at a lower number of clusters here. It's about 8. We're still going to choose 3. We'll try 4 as well, just so you can see the difference. But that's the elbow plot. That's one method of choosing the number of clusters that you're going to do for k-means, but it's got to be interpreted in the context of the problem, right? So if you have the elbow at, say, number of clusters is 10, but the complexity of your data set doesn't really warrant that number of clusters, then it doesn't make sense to choose that. So I'm just going to disregard the elbow plot essentially, but that is a method of choosing that. Now we're going to do the k-means clustering, and we're going to do this with number of clusters 3 to begin with, and then we're going to do it with 4 as well. So we start by, I'm going to write matplotlib.widget here, and the reason being is that I'm going to use a method of matplotlib to rotate the plots, and that was the import from before at the very start, this one here, axes 3D, that allows me to rotate the plot in 3 dimensions. That being said, while I'm recording, I'm not sure if it's going to be too laggy for that, but we'll find out. What I'm actually going to do is just copy the code in, and then I'm just going to explain it afterwards. I think that'll be a better way to do it. Now that I've copied it in, I can explain it. So, like before, I'm going to store this whole section here, which is what we're going to be doing k-means for, and we're going to store it into this separate data frame, or these 2 separate data frames. Essentially, we're going to be performing k-means clustering both for males and females, just in the same section. So here I've specified the number of clusters for both of them, so it's 3. And then this section here, we're just creating the instances of the k-means class. Then we're fitting k-means to the data, which is this one and this one, which is weight, height and age scaled. So same as before essentially. And yeah, exactly the same as before. So in this situation so I remember before actually that we created the cluster labels here, but that's kind of meaningless for the elbow plot. So we can actually remove this section here. Hopefully that didn't confuse you too much, but Because for the elbow plot, the labels are actually irrelevant. I remember now that the reason I had it there was because I used the silhouette score in my previous code. And for that, you do need the cluster labels. But just for the inertia score, you don't. Because it's already a part of the KMeans dot inertia underscore there. But here we create the cluster labels, and I'll show you what that looks like. If I just comment everything out here, run this code up to there. So the cluster labels look something like that. So it is an array, and because we have 3, we have the values 0, 1, and 2. So those are the, I don't think there's a unique thing for NumPy, no there's not. That's alright. But it's the values range from 0, 1, and 2. If we have 10, they would range from 0 to 9, and each value represents the cluster it belongs to. And then what we're doing is we're just creating a new column called cluster, and we're assigning these labels to that column. So then if we look at df KMeans male, which remember is just these values here, weight scaled, height scaled, and age scaled, it's going to have a new column, and that column is cluster. So now we can actually look at the unique values. So here we have 1, 0, 2. If we had 10, then the unique values would be 0 through to 9. Okay, now we're just creating a mapping of the cluster numbers to a color. So the reason I've gone from 0 to 5 is just because when I was testing this, I had a very different amount of clusters. It doesn't actually matter that we've gone down to 3, because it's just going to use 0, 1, and 2. In that case, it's not going to really look at this at all. It would be an issue if we went to a number of clusters greater than 5 later on in the code, because then we don't have a colors assigned to it. But anyways, this is a mapping, and basically it's just we're going to apply this mapping to the data frame, so that, or to that specific column, the cluster labels column, and that's going to be that's going to map all these cluster labels to various colors. The next code here, cluster, what was this? Cluster colors, xi for xi, cluster labels. Oh, okay, so essentially this is the mapping. Yeah. I believe that there's a map function or attribute maybe, but I didn't use it. I'm thinking I remember this right. I didn't use it, I'm pretty sure, because I had that issue with the multi-index data frame from before, and for some reason the mapping wasn't working because of that, because there was a multi-index. But I actually fixed the multi-index after that, but I kept the code the same for later on, but that's fine. So essentially this just runs through all the cluster labels, and it creates the an array of colors corresponding to each of those. So if we look at cluster labels here, we have 3, 3, and 2 for the first. Well, let's go up to 5. We have 3, 3, 2, 0, 8. Oh, hang on, we're on this again. 0, 2, 2, 0, 0. So that'll be blue, green, green, blue, blue. So then if we look at colors male, blue, green, green, blue, blue. It will be if I go up to 5. There you go. So essentially the array is just the array of colors male. That's just the array of cluster labels male, which is the cluster labels, the centroid labels, but just mapped from whatever number they are to whatever color they should be, and that's just going to be used in the plotting. So then we plot k-means. So we have everything to do that now. Create a figure, create 2 subplots, one for male and female, and This first one, for the males, that's a scatter plot of weight scaled, height scaled, and age scaled. I realize that maybe this was redundant here now because we're still using this anyways, these values, but keep it the same, that's fine. And then C is just colors male. So remember, colors male is just an array, and it's going to be the number of data points that there are. So every row of the data frame, which we get here, is going to be to a corresponding color, and that color is corresponding to the cluster label. So we're going to get a different color for each cluster, essentially, and that's going to be a way to see. That's actually that's just our way of seeing which cluster each points belong to. And then set title, X label, Y label, Z label, and then the exact same for the females, except just replace the male with female. If we run this, that's what we get. So hopefully it's not too laggy, but you'll see that I can rotate the plot. There you go. It's kind of pointless to rotate the plot if it's laggy like that. So the colors with each plot, they don't mean anything in relation to each other. The cluster labels are essentially just arbitrary. So the cluster 0 here doesn't really mean much in relation to cluster 0 here. That's why the colors don't really match up in the right place. But if we run it again just so that it gets back to normal. So we can see we have 3 cluster points here. And just quickly, if we interpret this, essentially, we can say that the green cluster here for the males, that corresponds to, it looks like it corresponds to where the weights and the heights are generally lower and the ages are generally lower as well. So younger people that weigh less and aren't as tall. The blue cluster corresponds to people that are average age, like maybe somewhere in the middle, because you can see it's a bit higher than the green cluster. And it's also people that are tall, and consequently they weigh a lot more. And then this yellow cluster here, that looks to be the ages that are even higher than that, with some down below, some on the same level as green and blue. It's hard to see this because just of the angle, and I'm not going to rotate it again just because it's going to lag. But it's about, some of them are quite tall, but the weights are about in the middle, essentially. So anyone that's obese will likely be in the blue cluster because that's where the weights are high. And the heights range from medium to high. So a lot of the data points are where they're tall, but about half the data points are where they're average height. But the weight is still, or average height, this section here, I should say. But the weights are still on this, the higher of the axes. And then for the females, we could do some sort of similar observation as well. It looks like it clusters it based on a similar principle as well. But it's pretty straightforward once you understand what I've said about the males, that to make an observation about the females. Let's change the number of clusters through to 4 and see how that changes it. But we can see that KMeans is a good algorithm to cluster this sort of data where it's clumped together and there's moderate differences between the data points, or at least there's some visual differences between the data points. The data points are still very close together across the whole data set, but there's some reasonable way to segment each of the data points so that they're in separate groups. And with this, it's people that are young who don't weigh much, who aren't very tall, which makes sense. There's another group where people who are obese. There's another group that people who are underweight, maybe. There could be another group where people are just of average weight, average height. And that's where K-means is a good algorithm, where the data points are clumped together, but there is a good way to there is like a meaningful way to segment the data. That's it. Well, that's the K-means algorithm. Now we're going to look at a violin plot. Looks like, did we not make one before? No, we didn't. I thought we did make it before. No. So we're going to make a bunch of violin plots. The first one is going to be for the inliers, and then we're going to do a violin plot for the outliers as well. I'll edit this part out, but I'll just copy the code in and I'll explain it. Okay, so for this first section here, we're doing a violin plot for K-means scaled, and actually it's not even K-means scaled, it's just K-means. You'll see what a violin plot is. It's better once I've actually plotted it. But what we're doing is we're creating the violin plot, and it's going to be the cluster label versus the weight, and then we're creating another one which is just the weight essentially, and that's just the Y point there. This is just specifying the colors. I don't really understand this too much, but the palette and the hue. But when I was watching, remember the video I referenced from before, from Trent Does Math, this is how he did it. So I need to look more into this, but essentially the main thing that's important here is these values here, X and Y. So it's going to be the distribution of the values of the weight, the height, and the age. I think I got this in the wrong format. So what do we have? Weight, height, age. There we go. That's it. So I'll plot it, and then you can see what's going on here. There we go. So with this first one here, male weight versus cluster, each of these violins here, they represent a specific cluster. So we have 4 clusters in this case. So we have 0, 1, 2, 3. And we could actually assign some meaningful name to each of these clusters. So for example, one of those clusters would be obese people, one of them would be underweight, maybe average, maybe young people. So we could do it like that, and actually we should if we do this cluster analysis. But for now, I'll just leave it like this. And then the way these work is that you get, for each of these clusters, you get a distribution of the weight. So essentially all we need to look at is maybe one of these sides of the violins. The reason that both of them are shown is just for aesthetic purposes. But if we cross out maybe the left side here, left of this bar, we get that distribution of the values. So for cluster 0, we get that the weight ranges from about 40 through to 120, and it's heavily skewed towards this area here, which is from about 70 through to 90, with bulk of the data happening from 80 to 90 over here. So that's what this hill represents essentially, or that the amount of deviation from this center here. And that's the same for each of these. So for this orange one, that's cluster 1. For this green one, that's cluster 2. And then this gray one is just the whole data set ranging from any cluster. So if you look back at the code here, for that one, that's this section here. This is the gray one. And that's just DF male inliers weight. So it's all of it. And the reason that we can... the reason that I didn't do the scaled version here is because then the values or the axes here would be meaningless, because it's just going to be the scaled version, so we can't really analyze it properly. So we use the scaled version when we're doing the K-means clustering, but then when we're visualizing it, we're applying the y-axis, or applying the non-scaled version to the y-axis. This second section, that's weights for females. So we have cluster 0, 1, 2, 3, and the whole data set. And then, does this make sense? Bit confused as to why this red cluster 3 is more than the whole data set. I don't really have an explanation for that. Do you have female inlies weight? Yeah, I'm not actually sure. There must be something, because I don't believe that should be what would happen. Or maybe there's something here that I'm missing. I need to look back at this. But anyways, we'll continue on. But I was doing a look. Yeah, it shouldn't be any less. This grey one shouldn't be any less than this than any of these points here. Okay, well, it happens in a lot of these. If anyone knows, then definitely write down in the comments, because I'm a bit confused at this. I'll look at this after the video, and if I remember, I'll create another video later on explaining what that is about. TF female inlies. Maybe it does have to be scaled. I'm just going to write the scale version here. Yeah, because I'm thinking that if we're putting the X value of the cluster, oh no, it doesn't have to be, because if the X value is all the cluster labels, and then this is just the same data frame but just not scaled, if we do it like this, then each row will correspond to the correct cluster. Yeah, alright, that's fine. We're going to continue. Okay, well that's the violin plot, and really I'm thinking that it shouldn't look like this. It should look different, but we're going to do the same one for the outlier analysis, and we'll see if this one definitely won't get that result, because we're only putting in, so these are the outliers, so we're just plotting DF male outliers weights, and then for females, and then heights for males, and then height for females, and then ages. So we can see that for the weight distribution, the outliers, there was only the one outlier, so we don't really get much of a plot there. It'll just be a line corresponding to where the outlier is. For women, it's there's no outliers for the weight, if you remember. Same as for height. Now for the males, there was some outliers for the height. Let's take a look at which ones those are actually. Yeah, we only have the two, which is 349, or what do we have? 1.98 and 1.97. So people that are tall. So yeah, that's corresponding to this bottom point there, and then 1.98, 1.97, 1.98. Yeah, that's corresponding to here and here. So when you have that little values, it's because it tries to create a violin. I believe that's why it's kind of it's not a good way to analyze the data if you have that little values, because then it's kind of meaningless. You can't really see, you can't really conclude anything from this plot. It's a much better way just to look at these values here and kind of conclude that, yeah, okay, so these outliers represent men that are really tall, and they weigh more than the average as a consequence, but I don't think they're obese. Maybe they I don't know. But yeah, they're definitely tall. So I mean, that's the way that I would analyze it. Now for ages, there's more data, if you remember. So the violin plot is more meaningful. So for the males, we can see that there's a bunch of data here. I think there's 20 something. And then for the females, if we just look at the info to look at how many data points there are, there's 96 entries, so 96 outliers. So these violin plots are a lot more meaningful then. Essentially, so for the females here, a lot of the outliers are down below here. So I guess a lot of the data points were heavily skewed towards the younger people, so that's why the outliers start from 35 onwards, and then you get some of the outliers up higher there. At least I'm hoping that I got this right, because otherwise there would be, yeah, so you can see that if we look back at the bar plot here from before, or the histogram, which is just the distribution of female ages, we can see that they're heavily skewed towards the younger people from 15 to about 30, and that's why the outliers are from 35 or whatever it was onwards. Yeah, 35 onwards. So for this one, it would make sense to analyze it in this way. And for the males, we could say, well, the outliers for ages, that's same across the board. There's really not much to say about ages. It was kind of, it'd be nicer if there were more outliers for height or for weight, because you could say something more about that. You could say, okay, well, these are tall people that are obese, or tall people that are normal, or tall people that are underweight as well. But then for ages, it's kind of, I mean, that's kind of like a variable that's doesn't really mean much in the grand scheme. Or I guess it could do. I mean, maybe a lot of, as you get older, it's easier to be overweight, and then if you're underweight as when you get old, that's probably not as common, or maybe it is more common. I'm not a biologist, so I don't know. Okay, we'll stop there. So that's a example for K-means clustering in Python. If you have any questions, write them down in the comments, or if you have any comments, write them down in the comments. Comments about my code, that is, or any of the concepts that I was saying, because I mean, I'm trying to learn this as well. You can see that some of the situations I didn't really know exactly everything about. Like, for example, if anyone knows about this situation here, then definitely write that down. Like why the grey violin can be less than one of the other violins. Maybe I think I got something wrong in the code for that to happen, because it doesn't make sense. Like for one specific cluster 3, it can't be any bigger than the whole data set, or it can't be any bigger either, but it can't be any longer. It can't range from 200 to 20, while the grey one ranges from 180 to 25. Thanks for watching.